Okay, so first let's talk about the learning target. So this is for chapter 16.2, and let's just quickly recap where we've been. In 16.1, we learned about the probability of an event occurring, and we learned about the probability of one event or another event occurring. And if, just as a quick review, to do that, we added those probabilities and subtracted off the intersection of them. And then this term would be 0 if the sets were mutually exclusive. If this didn't make sense, you can go ahead and watch the 7-minute review prior to this. The learning target of this lesson is actually to find the probability of events occurring together. So the missing piece from this list here is the probability of A and B occurring. And that's what we mean by occurring together. We want A and B to occur, not A or B. And so this right here is what we're going to learn about in this lesson. And then there's a secondary learning objective here about learning about independence. And we'll see that that's an important concept to be able to apply to actually compute the probability of two events occurring together. So one of the important tools in probability that we're going to use, especially when we're doing multiple events, is this notion of a tree diagram. I know we covered this quickly one time in a previous lesson in counting, but let's just make sure we have this down because we're really going to use this quite a bit with probabilities. And so to do this, I call it a warm-up here. Let's just think about a really simple experiment, tossing a coin twice and looking at the outcomes. So let's make a tree diagram. The way we're going to do that is we're going to think about each coin as its own separate event, and it really is. And so on a tree then, we're going to go ahead and draw out each event and see what the outcomes are. And the way to make this tree, you can make your trees up and down. I like to make them side to side. Since we have two different outcomes, the first set of the tree is going to be this heads and tails. So this row here is going to be the first coin, or column I should say. First coin, that says coin. And then once I've flipped that first coin, I'm in this head, if I have heads, from there I have two outcomes for the second coin. So that's what this next branch of the tree is going to represent, head and a tail. And I could have that same thing occur after I flip a tail on the first coin, a head or a tail. So that's what we mean by a tree diagram, and then each layer of the tree is going to be each event. And you could even imagine having a third and a fourth event and create and continue to draw your tree. And that's, again, something that we will encounter several times throughout probability. I'm just going to go ahead and write second coin here. Notice too how we can easily determine the sample space from this experiment by just looking down the branches. Really at the end of all the branches will be our sample space. So if we wanted to make our sample space, I'm going to go ahead and write that here. Again, remember, sample space means all possible outcomes. Well, here we just look down each branch. HH, that's one outcome. We look down this branch, HT, that's another outcome. TH, and then we have our last outcome, TT. And so here we have all the possible outcomes of throwing a die. Now you could have flipping a coin. You could have easily just written this out directly, but again, I think it's helpful to see how this thing comes out of a tree diagram, especially when the tree diagrams get more complicated. So then the next piece of the tree diagram I want to talk about is this notion of putting the probabilities onto the grid. The way we're going to do that is each branch of the tree, we're going to write the probability of going down each branch. And then that'll help us compute the probability of multiple events occurring together. So when you think about this first coin, I have a 50-50 chance. So I could have a 1/2 chance of going from here to the heads and a 1/2 chance of going to tails. Note how all my branches here add up to 1, because when I flip a coin I have to go someplace. And that'll be a theme through these probability trees, is that in a given layer all the branches have to add up to 1. And then we can move to this next layer and do the same kind of thing. So once I'm here, when I flip the second coin, what are the probabilities that for each of those things to occur? So if I'm standing here, I flip the head. In order to flip this head, I flip that coin, it's 1/2. Flip this coin, it's a tail, it's a 1/2. And then the same thing is going to be true here, and then the same thing will be true here. Again, notice how in this sub-branch everything adds up to 1, and how in this sub-branch the probabilities add up to 1. Okay, so here's where this tree diagram will become useful. What we really want to do is figure out what's the path of going through the down an entire branch, not just these individual branches. And so the way we're going to do that is you're just going to multiply down any given branch to get the probabilities. Now this example is going to end up being simple because everything's 1/2, but as an example, let's say I want to know the probability of going down the HH branch of this tree. Well, I just look at the probabilities and multiply them together as I go. And again, this is the multiplication principle at work. Remember the n1 ways, n1 ways, and 2 ways to do the second action. I have 2 actions. How many ways can I do them? Multiply them together. And that's really what we're doing in a probability as we're going down the branches here. So to get the probability of an HH, this is really the probability of going down this branch. So it's 1/2 times that 1/2. And that'll be our 1/4. And again, we got that by multiplying along the branch. Now this HT, how do we get that? Well, it's 1/2 times this 1/2. So the probability of HT occurring will be also 1/4. Now to get this TH, let's go down this branch, 1/2, 1/2. And then here, same thing, 1/2 times 1/2. The probability of tail, tail is also going to be 1/4. Notice how when I add all these up, they add up to 1. That makes sense. This is a sample space. This has to be all the possible outcomes. The probability of something occurring has to be 100%. Notice too, if I had asked the question, what's the probability of throwing one head or one tail, one head and one tail in my 2 tosses, I'd have to look at these sample sets here. Well, that one doesn't work. That's 2 heads. This one doesn't work. That's 2 tails. But both of these would satisfy that condition. So the probability of one of each would actually be 1/4 plus 1/4. Again, this is where I can add up the probabilities, and again, these are mutually exclusive. If I throw heads, tails, it's impossible that I threw tails, heads on that throw, so I can go ahead and add the probabilities without having to worry about subtracting off the intersection. So this is just a warm-up introduction to tree diagrams and how we're going to use them. Again, the key thing is to be able to draw the tree diagram, put the probabilities of each individual set of branches, and then be able to multiply through them to get the probabilities of traveling down the entire branch to the end. We'll see this again in the next example. Okay, so here we have a second example, a little more complicated, and I just want to go through this tree idea again. Here I've pre-drawn the tree, and just to go through the example, we have a jar of 5 balls. 2 of them are red, 3 are green, and they're in a jar. So we want to use this tree diagram to determine the probability that we draw 2 balls of the same color. So when we grab in and take 2 out, either it's going to be 2 reds or 2 greens, nothing different. So again, we've represented this by a tree diagram. When I pull out the first ball from the jar, it can be either red or green. Now again, the way we're going to do these tree diagrams is go ahead and write the probabilities. Well, there's 2 red ones and there's 5 in total. So here we can go ahead and just write 2/5 on that branch, and then the probability of getting green is going to be 3/5. Now, here's where we have to do a little bit of thinking. We have to separately evaluate each one of these options. So if we're down this tree here, the first ball we've chosen is a red ball. So when we think about what's left, well, there's 4 balls left in the jar at this point, and one of the red ones is gone because on this branch of the tree, we've already selected red. So when we have to think about that when we set up these probabilities. Well, the probability of drawing another red ball is, well, there's 4 balls left in the jar, and there's only 1 of them that are red. So the probability of drawing this red ball is going to be 1/4. The probability of getting green on that next draw is going to be 3/4. Again, see how these add up to 1. Again, it's just like we saw in the previous example. These also add up to 1 on this set of the branches. Now let's think about what happens if we draw a green ball first. Right on this branch, we've drawn a green ball. Well, what's left? Well, we still know there's 4 balls left in the jar. But if we've drawn a green ball first, now that means there's 2 reds left. And so this probability on this branch is 2/4. And then similarly, the green ball, 2/4. Again, this adds up to 1 here. And so we've created our tree diagram. Now, again, we want to think about our sample space, and let's just go down all the different branches of the tree. We have RR, RG, GR, and GG. Now just think about the probabilities of them. We multiply through down the branches. So the probability of this RR event occurring down the two branches, 2/5 times 1/4. Again, we always multiply down the branches. 2/5 times 1/4. That's going to be 2/20. Not sure why my pen just changed color there. That was strange. And similarly, the probability of RG, we multiply down the branches, we're going to get 2/5 times 3/4 for this one. Probability of GR, now we're in this branch, 3/5 for that first G times 2/4 for the R. Then the probability of green is going to be 3/5 times 2/4. Go ahead and switch that to blue. Multiply that one out. The reason I'm only multiplying the top and the bottom one, the probability that we're really seeking here is that two balls of the same color are chosen. Well, that's going to be this event and this event. I find the probability of them by multiplying through the tree 2/20 and 6/20. And to finish off this problem, I just go ahead and use the addition principle and add them together to get 8/20 or 2/5. So an important thing to notice here is, think about the second ball we drew out of the jar. The probability whether it was red or not depended on what the first ball was. Here, the probability was 1/4 if the first ball was red. Here, the probability of that second ball being red was 2/4 if the first ball was green. And so that motivates this notion of needing to describe something called conditional probability. We can only describe the probability of this occurring based on what happened, conditioned on what happened previously. And the notation we're going to use for that is this slash bar in there. So like what we're going to think about this is the probability of that second ball being red given that first, switch colors on me again, first was red. And then we could also think about what's the probability of a red ball occurring given that the first was green. And so that's what, when we get names to these probabilities, that's what this one's going to be called. The probability of red given that the first was red, and then this one would be given this name here, probability of red given that the first was green. In a generic sense, we're going to write the probability of an event B given A, or conditioned on A. And so that's what this notation is going to mean, is what's the probability that B occurs given that I know A already occurred. And that's going to be called conditional probability. And as you can see, when we want to think about the probability of two events occurring together, it's going to be important to factor in what might have happened previously in order to figure out on the first event, it's going to be important to understand what happened in the first event in order to determine the probability correctly for the second event. Finish writing that off. Conditional probability. So here I'd also like to just quickly introduce the concept of independence between two events. You can see in that coin example that we had done that the first coin didn't really impact the probability of the flip on our second coin, and we're going to call that kind of situation independent, that the two events are independent. So the way we're going to see that that can happen is if the probability of B given A occurring turns out to be the same as the probability of just B occurring, we're going to call that situation independent. And we're going to call A, it means A and B are independent. One does not influence the probability of the other. So this will be our definition of whether two events are in fact independent. Okay, so just to re-summarize this notation here, under conditional probability, this little slash here means conditional, and the way we're going to read this is the probability of B conditioned on or given that A occurred, and that's the notation there, and it just means the probability that this event occurred, B, given that A has already occurred. And then this notion of independence is shown in the second line here, which we're going to think of as, again, if the way it's, the reason it's independent is if if the probability of B given that A occurred is the same as the probability of B occurring by itself, that means A doesn't matter. It's not influencing the probability of B occurring. And so that means we're going to call those independent. Because again, if the two events are dependent on each other, that means that one happening will influence the probability of the other one occurring. We'll do examples of this in class. So now we can move on to really summarize what the learning target for this particular lesson was. Again, remember, we're trying to figure the probability of two events occurring together, the probability of A and B, or we can think of this as the probability of A intersect B. Same thing. Well, so now we have the tools we need. For any two events, A and B, the probability of A and B occurring, think of the tree diagram. The first thing that's going to happen in the tree is A is going to occur. Right? If we have A and B. But now to figure out this next branch on the tree, we have to know, we know that A had already occurred. So the probability of B occurring, we have to do given A, because that was the branch of the tree we were on. So in order to figure out A followed by this particular B, we have to, again, we multiply down the branches, but we have to make sure to put the conditional probability here, because this was our first pass down the branch, A, and then the next event is B, but we already know we were on the A branch, and so we have to do the probability given A in order to figure the two events. This will also work the other direction too, the probability of A and B. We could easily have chosen B first, and then in this case we just have to change the sequencing that the probability of A given B occurs. And this identity will end up being used at some point when we do some other conditional probability problems, but again, you should see that it's equivalent to write this either way. It doesn't really matter which one we choose to happen first in terms of two events happening together when we write these probabilities. And then for any two independent events, this is where things get a little easier. When events are independent, then we simply just have to multiply the probabilities. But this is the only time we get to actually just multiply them without having to worry about this conditional. And the way to see this was, remember this probability of B given A, well, it just equaled probability of B when they were independent. And so we can just replace, we're just taking this top formula and replacing it with probability of B. A lot of times events will be independent, so this will be a really simple way to figure out the probability of them both occurring. We multiply them. And that'll occur quite a bit actually, where this notion of and will be associated with multiplying, and then a lot of times with or, it'll be associated with adding. Remember, we had if we did the probability of A or B, there we actually got to add them. Now if they were, we might have to worry about the intersection here, but you know, the basic operation of or was to add them together. The basic operation of and is to multiply them together. Okay, so let's do a couple quick examples here. This first one is we see a student in a class, each student in a class of 30 studies of one foreign language, French or Spanish, split in this table here, 14 in French, 16 Spanish, and then they study one science, 8, 10, and 12 between chem, physics, and bio, all adding up to 30, and so all the students fit in exactly one of these cells. So the first question here is, what's the probability that a randomly chosen student studies chem? Notationally, we're going to call that the probability of C, studying chemistry. Here we can just use our counting principles because each student is kind of an equally likely outcome. And so we know that there's 30 students in total, and then the number of students satisfying the event chemistry is this total of 8, and that would be it. We'd be done with that part of the problem. The next one is, what is the probability that a randomly chosen student studies chemistry given that the student studies French? This term given here should clue us into the fact that we're going to need to worry about conditional probability. And so the way we're going to write this notation is the probability of the student studying chemistry given that they study French. Let's think about this the intuitive way first. So the intuitive way to think about this is that we're going to limit ourselves to just the people in the French line here. Since it's a given that we chose the person in French, we can ignore the rest in determining this probability. So we know that the total outcomes in this case are now 14 because it's given that we know we're in this first row. And then once we're in the first row, we know that the number of students studying chemistry is 7. And so the probability of someone studying chemistry, given that they've studied French, is actually 1/2. Now, if I want to do this problem, I'll call it the longer way. We can just derive this expression from the basic formula for two events occurring together. So if we have two events here, chemistry and French, C and F. Well, what's the probability of two events occurring together? We know how to do that. It's the probability of one of them occurring, I'll pick French, times the probability of the other one occurring, given that the first thing I picked happened, C given F. I chose French here because this is the one I'm interested in. If I went ahead and rearranged this expression, we could see that the probability of C given F is just going to be the probability of C and F divided by the probability of F. This will be an expression we'll end up using a fair amount. But then we can go ahead and just use the probabilities that we need from up here. So the probability of French is actually going to be, again, now probability of French is looking at the entire student population. That's going to be 30 out of 30, 14 are French, studying French. And then the probability of studying chemistry and French, again, it's the same 30 in the population, but now C and F, you need to look at this cell right here, 7, because chemistry and French, that's the only group of this 30 that's studying both. 7/30ths over 14/30ths, these 30s cancel, and not surprisingly, we still get that same 7/14ths that we did over here in the intuitive way, or 1/2. But I think it's instructive to see this particular formulation of two events occurring together because it allows us a way to solve for the conditional probability. It's always going to be the ratio of the two things occurring together divided by the probability of the event that's being conditioned on, in this case, F. And then the last question here are the event studies French and studies chemistry independent. Well, so the question is, does one depend on the other? Well, we can just use the two results from above to check that out. This is asking, is the probability of studying chemistry the same as the probability of studying chemistry given that I study French? If this is true, then they're independent. If true, independent. Well, we have the two pieces up here, so the question is, was 8/30ths, so that was the probability of studying chemistry, equal the probability of studying chemistry given that you studied French, 1/2. Well, no, these are not equal. So we would say these events are not independent. Okay, and our last example here is we have this middle school. We have 18% of students play football and basketball. So I'm going to go ahead and write this as the probability of basketball and football. It's changing colors on me. B and F equals 18%. And then we know that 32% of all students play football. So the probability of playing football is going to be 0.32. The question here is, what's the probability that a student plays basketball? So we're looking for the probability of basketball given that a student plays football. So this is the target thing we're looking for right here. And we can use that same approach that we just saw above, where we know that the probability of B and F is going to equal the probability of one of them occurring. We'll pick F in this case because we're looking for this target here, times the probability of the other one occurring given that the first one occurred. Well, do we have everything we need here? Well, we have 0.18 is the probability of both occurring. Probability of playing football is 0.32. X is what we're looking for there. So in this case, we're going to be looking for 18.18 over, and that's going to simplify to 9/16. Another way to visualize why these problems work this way is to think about a Venn diagram. If I go ahead and draw this Venn diagram for football and basketball, put basketball here, football here. Well, we know 0.18% of the kids lie in this little football shape here. And then we know the total football is 0.32. That would give us 0.14 of just plain football. But from a visual perspective, really what we're trying to do is, given that we're playing football, we're trying to find probability of basketball given you play football, we're going to limit ourselves to this circle right here. So that total circle is 0.32. And then we're just trying to find what percentage of the circle is inside here, given that I'm in the circle. And that's another way to see why we get the 0.18 over 0.32 or 9/16 from this formula. So you can kind of see it visually. Once we have the given condition, we zero in just on where we're given, and then we go ahead and find the probability. And that's why it's 0.18 divided by this entire circle of 0.32.